let's resume our discussion of differential geometry in Euclidean space. We were talking about curvilinear coordinates, natural basis vectors obtained by taking the derivative of a position vector with respect to curvilinear coordinates. We spoke about dual basis elements and so on. And we introduced the notion of a metric, dual metric, and here we are. And ways of representing vectors and tensors in terms of co- and contravariant components. The identity tensor. We talked about coordinate transformations, formulas. For example, this one, for a second order tensor, the covariant components transform in this manner. You can quickly deduce the transformation formula for any set of components, mixed, contravariant, and so on. Okay, we ended at this point. Let's begin here. We will need to have representations for various important differential operators that arise in our subjects, such as gradient, divergence, and so on. The gradient of a scalar field, for example, is the vector which, when dotted with dx, gives you d phi. That's just the chain rule that we've seen before in connection with, say, the deformation gradient. Here we're talking about a scalar field. The chain rule, if phi depends on the coordinates, theta super I, then d phi is also phi comma I d theta I. This is a partial derivative. D theta super I, remember, can be written as grad theta super I dot dx, again by the chain rule. So now we're able to factor out the dx from both sides of this extended equation. And we conclude that the gradient of phi must be phi comma I of g super I. So the covariant components of gradient phi are the partial derivatives of phi with respect to the coordinates. The contravariant components can be obtained by simply regarding g super I as the index raised version of the g sub j using the dual metrics. We have here the contravariant components, the jth contravariant component of the gradient of phi is g super ij phi comma I, sum on I. So we have these two representations for the gradient of a scalar field. The gradient of a vector field is, again, by the chain rule, it's that second order tensor, grad v, which operating on dx gives you dv. If v is a function of the curvilinear coordinates, then by the chain rule again, dv is v comma I d theta I, partial derivative. D theta I again is g super I dot dx. And now we recognize this as a tensor product of two vectors operating on dx. But of course, you have two vectors one at a time. There's a sum on I, so actually three tensor products here inside that parenthesis. So if this being true for all dx, it must be the case that gradient v has this representation. The partial of the vector with respect to the ith coordinate, tensor product g super I. Well, we can decompose that further by writing the vector itself in terms of components, for example, in terms of contravariant components. And now we have to take the derivative of everything here using the product rule. The g's will, of course, now depend on the coordinates in general in our curvilinear coordinate system. These derivatives would be zero in a Cartesian basis, the orthonormal basis associated with the Cartesian system, but not in a general coordinate system. To represent these, well, we can represent each of these vectors, g sub j comma I, the partial with respect to theta I, in terms of any basis element we wish. For example, we can represent them in the basis g sub k. The way we do that is we project the vector into the dual basis and then multiply by the natural basis, sum on k. This is the standard formula for any vector. Any vector v is the projection of the vector in the dual basis multiplied by the natural basis, or vice versa if you prefer. you can project the vector into the natural basis with a subscript and multiply by the dual basis element, G super K, if you wish. In this representation, so inside this parenthesis, we have a collection of functions, not vectors, but after the dot product, we have functions. We'll call these gamma super K sub Ji inside the parenthesis. So there are 27 of these altogether in our three-dimensional space. I should mention a convention that we're using here is that the subscripts Ji are in the same order as the J and I on the left-hand side. J on the left, I on the right, here J on the left, I on the right. Some authors in the literature, if you'll see, use the opposite convention with an I first and a J second. And that leads to slight differences in formulas that you should be aware of. So you should be aware of the convention being adopted in whatever papers or books you're reading. The convention I'm using here is quite commonplace, and we will strictly adhere to it in this course. Okay. These gammas are called the connection coefficients. The reason being, if you think of if you remember the subscripted G's, these are tangential to the coordinate curves. So we can think of these as a basis for the tangent space of our manifold at a particular point. This formula then, if we know the gammas, it tells us how that basis, that tangent basis, changes from point to point in space. So it effectively tells us how the tangent spaces are connected to each other at adjacent points. For example, they tell us how the tangent basis changes as we move from a point P, say with coordinates theta I, to an adjacent point Q with coordinates theta plus d theta, right? Because these derivatives would then give us the change in the basis elements at first order in the d thetas. So in effect, they tell us how to connect the two tangent spaces at P and Q, hence the name connection coefficients. You will encounter a number of different names for these coefficients, depending on the context. For example, Christoffel symbols in honor of a German mathematician named Christoffel. And also, as, you'll see the name Levi-Civita connection coefficients. Levi-Civita is a famous Italian mathematician who worked to lay the foundation of tensor analysis and differential geometry. He was a student of an Italian mathematician named Ricci, R-I-C-C-I, who really organized tensor analysis and differential geometry into a major branch of mathematics. And in fact, the subject really became widespread due to the efforts of Einstein in using this formalism to understand the nature of gravity in four-dimensional space-time. He was compelled to learn the Ricci and Levi-Civita calculus so that he could develop the mathematical theory of gravitation. And it's thanks to Einstein's application of these ideas in physics that in modern times we have benefited so much from applications of tensor analysis and differential geometry in physics, and in particular in mechanics. Okay, so we have this somewhat ungainly collection of coefficients. In 3 dimensions, there'll be 27 of these altogether because each index ranges from 1 to 3, so we have 3 to the power 3 coefficients, 27 coefficients. But in our Euclidean space, we can reduce this number dramatically because if you recall, gamma super K sub Ji is G super K dot G sub J comma I, but G sub J is itself X comma J. And then we have two partial derivatives, d squared X d theta J d theta I. if this parameterization of the position is twice differentiable, then we can interchange the order of the partial derivatives without affecting the result, which means that these gammas are symmetric in the subscripts. So Euclidean space is an example of a space in which the connection coefficients are symmetric in the subscripts. In fact, that property is also true in more general kinds of space, such as so-called Riemannian space, which is exemplified by four-dimensional space-time theory of gravitation. So in the Riemannian space associated with Einstein's gravitation theory, the connection coefficients, which arise due to the presence of gravity, are also symmetric in the subscripts. In two dimensions, if we talk about the intrinsic differential geometry of a surface in two dimensions without regard to the three-dimensional space in which the surface resides, that's also an example of a Riemannian space, which furnishes another example of a space in which the connection coefficients are symmetric in the subscripts. Whenever you have this property of connection being symmetric in the subscripts, we speak of a Levi-Civita connection, and that is the basic geometric object in, for example, the theory of gravitation. While we're on that subject of more general spaces, more general than Euclidean space, an example being a Riemannian space, I should mention that the notion of connection is really, at a basic level, is only defined on curves in the space rather than in the entire space. So, for example, if we parameterize a curve by giving the coordinates of the manifold in terms of a single parameter, we have a parametric equations of the curve, then the notion of connection is really given by this equation. This is an ordinary differential equation, which determines how the g's, the tangent basis elements, change as you move along the curve. And these omega, this matrix omega ji, sum on j, tells us, if we know this matrix, it tells us how the tangent spaces are related to each other as you move along the curve. You can always integrate this equation if you know the omegas on the curve. And if you have an initial condition for the g's at some point on the curve, you can always integrate this system of three ordinary differential equations on the curve, and you will get a unique solution for the g's on a given curve. Euclidean space, and also all the spaces that we'll study here in the course, including the space-time of relativity, these are all examples of what's called an affinely connected manifold, or affinely connected space. An affinely connected space is one in which these omegas, these coefficients, are linear functions of theta dot, the derivatives of the thetas with respect to the parameter. So such a linear function will look like this: some collection of coefficients times theta dot k. These are the connection coefficients we've just talked about in our example of Euclidean space. And these are defined then in the enveloping space, the gammas. In this case, this system of ordinary differential equations becomes this. Or if we think of multiplying through by dt, where t is the parameter, it's just dg related linearly to the d theta k's, like so. So these are differential equations defined on a curve. They can be integrated on the curve, always. A separate question is, does this give rise to the existence of g's defined in the entire surrounding space? In other words, can they be integrated to yield functions gi of the coordinates in the enveloping space? If so, then we say that these equations are integrable in the space. So if these equations are integrable in the surrounding space, then the dg's are just given by the partial derivatives of the g's as function of the coordinates times the d theta k's. And so the left-hand side of this equation becomes just simply this. Integrability would mean that no matter what curve we consider here, we can always find the g's in the enveloping space. That means this would be true for all d theta k's, that is for all directions theta dot k. In that case, we have these equations, which is how we started our discussion. So we then have gi comma k given in this manner. If we stipulate in addition that our space is Euclidean, then the connection coefficients are symmetric in the subscripts. By the way, so this certainly holds in our Euclidean space with a symmetric connection, because that's how we constructed these in the first place, by starting with Euclidean space. In a Riemannian space, this does not generally hold. And so in a Riemannian space, these equations are not integrable, although they can be used to define a derivative of vectors. Okay. Later on, when we apply these concepts to plasticity, we will see that we can associate plastic deformation with an equation of this type, in which the gammas are not symmetric in the subscripts. That is, gamma sub ik is not equal to gamma sub ki. And so then we have an example of a non-Euclidean geometry, and we'll see that asymmetry in the subscripts is associated with a density of dislocations induced by plastic deformation. So we can associate quite an interesting geometry with plastic deformation. And by the way, here we mentioned only the so-called affinely connected spaces, in which these omegas are linear functions of the directions theta dot k. One can contemplate also a more general space in which those omegas are nonlinear functions of the theta dot k's. And that's called a Finsler space, or a Finsler geometry. And there have been some occasional applications of Finsler geometry in mechanics and relativity and so on, more general notions of relativity, and also applications in mechanics. This has recently become a more widely investigated topic in mechanics, the topic of current research, in fact. Okay, that's a long enough digression from our main task. Let's go back to our discussion of the gradient of V in our Euclidean space. We arrived at this point. Now we can represent these derivatives of the g's in terms of the connection coefficients. Relabel the summation index from j to k so that I can group the terms together in a parenthesis. In this parenthesis, to save writing, I'll simply use a different notation to represent that parenthesis. I'll use this notation: V super k semicolon I. And that's simply defined to be the parenthesis. Okay. That's called the covariant derivative of V super k. So that altogether, if you remember that gradient V is this, and now we have a formula for V comma I in terms of these covariant derivatives, we have now this representation of the gradient of V in terms of these so-called covariant derivatives. And this should remind you of the expression for the gradient of V in, say, in Cartesian coordinates, where we just have partial derivatives and then a fixed orthonormal basis that does not vary with position in space. It has the same appearance, except that the comma here is replaced by the covariant derivative, and we must be careful to sum only on diagonally repeated indices. Well, we could start, if we prefer, with the covariant representation of the vector V in terms of covariant components, and then take the partial derivative. Then we will encounter the need to differentiate the dual basis elements, as indicated here. Again, we can resolve these in any basis we choose. For example, we can resolve them in the dual basis at a particular point. We do that by projecting the vector into the natural basis elements and then multiply by the corresponding dual basis elements and sum on k. That's just another application of the standard representation for any vector. Right? So these derivatives evaluated at any particular point are just a collection of vectors, so we can use that same rule again. It appears now that we have another collection of objects, right, functions, indexed with 3 indices. In fact, we can compute these in terms of the original connection coefficients. We can do that by differentiating this reciprocity relationship, or duality relationship, giving the dual basis dot product the natural basis elements as the Kronecker delta. The left-hand side, of course, being zeros and ones are constants in space. So if we differentiate this equation with respect to theta super I, let's say, you'll get 0 on the left, and then you'll get this plus g super j dot g k comma I, which we know how to represent in terms of the connection coefficients. So solving for these, we get just the connection coefficients with a minus sign now. And if we put everything together in this expression, using this representation now with a minus sign, we get an alternative expression for the derivative of the vector in terms of this collection of terms. We'll call this vk semicolon I, v subscript k. That's another covariant derivative. It's also called the covariant derivative. The difference now being that we have a minus here in front of these terms. Okay? And so we have an alternative representation of the same gradient vector in terms of these alternative covariant derivatives. This is all, of course, too much to remember. One convenient device for remembering the structure of a covariant derivative is that the second index, according to our convention we've adopted, the second index here always corresponds to the index of the derivative, I, consistently in each term. The second subscript corresponds to the index of the derivative. You see the same is true here. The second subscript on the connection coefficients corresponds to the index of the derivative. And then, to complete the expression, you retain the superscript k on the connection coefficients, and then do the only remaining thing, which is to combine the components of a vector in a sum. So the sum must pertain to diagonally repeated indices, so you must have the contravariant v here to go with the lower index on the gammas. And the same notion here. You must have a covariant v to go with the superscript j here, right? And then the k and I are preserved in each term. Okay. With these representations, we can find a representation for the divergence of the vector. By definition, that's the trace of the gradient of a vector, which of course itself is a second-order tensor. Using the first representation for the gradient, right, we had here, let's say, this one here, take the trace of this. The trace operator has the effect of converting the tensor product into a dot product. So we'll have a g super I dot g sub k, which is the Kronecker delta. Sum on k, for example, and we get v super I semicolon I. Notice that we can write v super I as the index raised version of v sub k using the dual metric. So this is another way of writing the divergence. We could have started with the alternative representation of the gradient and take its trace. We get g super k dot g super I, which is the dual metric. So we have this alternative representation. And it's not immediately obvious that the right-hand sides are the same as they must be, because the left-hand sides purport to be the same quantity. In fact, we'll see in a moment that the g super k I have zero covariant derivatives, and also that the covariant derivative obeys the product rule, so that in effect we can factor out the covariant derivative from the duometric from the covariant derivative. So we'll see later why these two right-hand sides are the same, in fact. Proceeding with our notion of differential operators, for example, the Laplacian of a scalar valued function, by definition, that's the divergence of the gradient. This gradient phi, of course, is a vector. We know the gradient, we need to take the gradient of that, that's a second order tensor. The gradient of that is grad phi all comma I, tensor product gi. That gives a second order tensor, and then we can take its trace. The trace converts the tensor product to a dot product. Then now we can take the partial derivative of the entire vector, grad phi. We do that here in this next line. We encounter again the derivatives of the dual basis elements, which bring the negatives of the connection coefficients as before. Change the summation index here to a k so I can collect all these terms in one parenthesis. I have g super k, g super I, which gives me a duometric g super ik, or ki is the same because of symmetry. Notice that if phi is a C2 function of the coordinates, then the partial derivative is symmetric with respect to k and I, right? Phi comma ki is the same as phi comma ik. In our geometry, Euclidean geometry, we have symmetry in the subscripts ki of the connection. That means this second covariant derivative of the scalar is symmetric in the subscripts. This would not be true in a space in which the connection is not symmetric in the subscripts. Okay, for example. We will also need the notion of divergence of a second order tensor. For example, the equations of motion involve the divergence of stress, which is a second order tensor. The divergence of a tensor, here's the standard definition of that divergence. Divergence of a second order tensor is itself a vector, which when scalar multiplied by any fixed vector c, constant vector, is the same as the divergence of this vector A transpose operating on the fixed vector c. We know how to compute the divergence of a vector. That's just given here, gi dot v comma I. V now, we need the comma I is A transpose comma I c, and then c is fixed, so there's no derivative of c. We can use the definition of transpose to rewrite this with the transpose of this tensor to the left of the g, then dotted with c. I want to do that because I want to isolate a dot product with c so I can compare with the left-hand side. It's easy for you to show for yourselves that the operation of taking a derivative of a tensor with respect to a parameter commutes with the transpose. So we can take the derivative of the transpose or the transpose of the derivative, they're the same thing. And then if we add the further transpose by interposing here, we recover simply the derivative of A transpose transpose, or A. Okay? So now we have isolated a dot product with C. Let's fix a particular point in space, P. Then the divergence of A at that point will be some fixed vector. This combination here at the same point will be another fixed vector. And so the difference will be some fixed vector. So this is an admissible choice of the vector C, which is arbitrary. So we can make this choice. This equation then tells us that the squared norm of C, C dot C is 0, so the norm of C is 0. C must be 0 then, in which case divergence of A is just this, where I've relabeled the summation index for convenience. Now, so in this formula, this is an easy to remember formula for the divergence in any coordinate system. I can write it in terms of components of the tensor. For example, if I represent the tensor in terms of its contravariant components in this way, I have these three tensors obtained by taking the J derivative. On each one of those, I multiply by the corresponding dual basis element and sum. Well, in this partial derivative now, you have the partial derivative of the components, and then you encounter the need for the partial derivatives of the natural basis elements. You have a partial derivative of this first basis element will bring in a set of connection coefficients. And then the second one will bring in another set of connection coefficients. So altogether, you'll have two sets of connection coefficients in the final result. So you can summarize the final result in this way, where this is effectively a covariant derivative now of the contravariant tensor components. Notice again, the index of the derivative corresponds to the second subscript of the connection coefficients. Each contravariant index brings in a plus an associated set of connection coefficients. Okay. Here I goes with I, and then you have a summation K left over here, and then you have K here and an I here. Okay. Now, when you're finished with that operation, you must operate on the tensor G super J. That gives you a dot product G sub K dot G super J, which is the Kronecker delta super J sub K. I can sum on K, for example, and I will get A super IJ semicolon sub J. You obtain this simply by putting K and J, K equal to J, and summing over here. An alternative is to start, instead of using the contravariant components, instead start with the covariant components. If you work through the same exercise, you will get this result here, where we now have a different kind of covariant derivative based on the subscripted A's. When we do this, we will have to differentiate the dual basis elements, which will bring in the negative connection coefficients. Okay? And you can do the same with the mixed components of the tensor. You can use left mixed or right mixed components, and you can derive alternative covariant derivatives. Using this formula, we can deduce something of major importance in the subject. For example, let's take the conventional partial derivative of the metric components, recalling that the metric components are the dot products, the scalar products of the natural basis elements. Okay, so we use the conventional product rule now for partial derivatives. Each of these derivatives brings a set of connection coefficients, and then we dot with the remaining basis element, and we get two terms like this, because we're differentiating two sets of basis elements. Okay? If we can compare this with this equation here, this means simply that the covariant derivative of the metric is 0. Bring this right-hand side to the left-hand side, and you simply have this equal to 0. So this, by the way, is called Ricci's lemma, the same Ricci, R-I-C-C-I. In the same way, we can establish that the covariant derivative of the dual metric using this formula for covariant derivative, that's also 0. These results are only to be expected because you may remember that the metric coefficients, either covariant or the dual ones, are the components of the identity tensor. And the identity tensor is fixed in space. It has no partial derivative. Partial derivative of the identity is 0, so you expect the associated covariant derivatives of the components of the identity to be 0 as well. We'll come back to this result in a moment. It transpires that we can compute the connection coefficients in terms of the metric and its derivatives. To see that, let's make a definition. We see here we have metric multiplying by connection coefficients. Let's agree to lower the index L in this manner. In other words, I will define gammas with subscripts, like so, to be the result of lowering the index L in this manner. When I do so, it's important to keep in mind that in my definition, the J appears in the first position. The reason is I want to group the IK terms together, keep them together, adjacent to each other, which will help me to remember that because of the symmetry in IK here associated with our Euclidean space, these will also be symmetric in IK. So this is merely a definition, which allows us to rewrite this right-hand side in this more simple notation. I can take this equation now and simply permute the subscripts. So I can write, instead of IJK, I can write JKI, and I get this simply by relabeling the indices appropriately. And I can permute them again, and I have this. And this seems like a pointless thing to do, but let's be patient. For example, if I add the second and third lines together and subtract the first line, I see that I will get this combination of terms. This is important because the symmetry in the second and third subscripts can now be invoked. This term will annihilate this one, and this one will annihilate this one. Here we have a sum, so these will combine. This one is the same as this one because of the symmetry in the second and third subscripts. So I'll get a factor of 2 here. So this here is just a restatement of what I said, that the gamma is symmetric in I and K. I can interchange I and K because of the symmetry in the lower subscripts of the original connection coefficients. So that allows me, the factor of 2 I can bring to the other side of the equation, and I have the subscripted gammas determined entirely in terms of the partial derivatives of the metric. I would like to solve for the original connection coefficients, and I can do that simply by inverting this formula here. Right? This can be inverted to find the original connection coefficients in terms of the subscripted connection coefficients. I can do that in this manner. For example, I could rewrite this using the Kronecker delta, sum on L, and use the fact that the Kronecker delta, which is the unit matrix, is the product of the two matrices consisting of the metric and the dual metric, because these are inverses of each other. And then this combination here is simply the subscripted gammas, which I now know from this line. So to get the original connection coefficients, I simply multiply by G super MK. So now I have the connection coefficients determined. If I know the metric, I can compute the dual metric, take the partial derivatives, and I have these connection coefficients. You'll notice that there's a symmetry with respect to interchange of I and J. That symmetry is evident here. It's also here because G sub JK is the same as G sub KJ. So I have a KJ comma I and a KI comma J. That combination is symmetric in I and J. A connection with this structure is called the Levi-Civita connection. And it's this formula for the connection also underlies the Riemannian geometry. For example, in the 4-dimensional theory of gravitation or the 2-dimensional theory of curved surfaces. These are examples of the Riemannian geometry. And Riemannian geometry, the Levi-Civita connection is the appropriate connection in that geometry, or the characteristic connection. So the Levi-Civita connection, of course, also pertains to our Euclidean space. We've never left our Euclidean space in this discussion. There's a very nice property of the Levi-Civita connection, which is the following. So let's take the 2 on the other side. Let's contract in the index I, that is to say, replace m by I, and then we have an I downstairs as well, so we are forced to sum on I. Gamma I, ij, so we simply replace m by I, we have this on the right. Distribute the product in each term, we have this. In this last term, I will exploit the symmetry G super ik equals G super ki to write it in this form, the last term, only in the last term. The reason for doing that is notice that k is a summation index and I is a summation index. We can relabel these summation indices as we please. For example, I could rename k, I could call it I, which means I have to replace k by I consistently. I could rename I could call it k, and then replace I by k consistently. And then I notice that this term is exactly the same as this, and so they cancel each other. Again, I'm using the symmetry G sub jk is the same as G sub kj. So these cancel each other. So that means this contracted connection coefficients is given by this. We can remember, if we introduce the determinant of the metric, call it G, the determinant of the metric, the matrix of metric coefficients, then if we remember from matrix algebra, matrix calculus, the derivative of the determinant with respect to the matrix element is the corresponding cofactor element. The cofactor is the determinant times the transpose of the inverse. The inverse is symmetric, so it's equal, we have a symmetry in I and k, right? So it's just the determinant times the inverse. The inverse is just the duometric. So we can write the duometric as 1 over g times the derivative of the determinant with respect to the metric. And of course, we carry the factor of 2. Now this, dg, gik, comma j, is just the chain rule representation of g comma j, right? G depends on the coordinates via the metric. G is the determinant of this, right? So it can only depend on the coordinates through the elements of the metric matrix. Okay? And an even simpler way of writing this is to rewrite this as 1 over square root of g, all comma j. We recall that square root of g is positive, or rather g is positive in our formalism here, so we can take the square root. That's because our metric was positive definite, if you recall. Okay. With this in hand, now we can have a simple formula for the divergence of the vector field. Remember that was v super I semicolon sub I. If you look back at the formula for this covariant derivative, you put the superscript and the subscript the same, I, you will get the gamma with I upstairs and downstairs, which we've just computed. And if we use the symmetry in the subscripts, Ij is the same as Iji, then we can rewrite this as the second line and factor out a 1 over square root of g, and we just have this expression, which involves only a partial derivative here. So this is a much simpler formula to remember for the divergence of a vector based on the contravariant components of the vector. The Laplacian then, if remember that Laplacian is the divergence of the gradient of f, the scalar value function f, we can set v equal gradient f then we need, in this formula, the contravariant components of V. That's given this way. As we've seen before, these are the contravariant components of the gradient of F. Simply insert these into this formula, and we have a nice, elegant formula for the Laplacian in an arbitrary coordinate system. Of course, there's a double sum, interior sum on J, and then an exterior sum on I. Okay, it's time for an example, perhaps overdue. Let's compute an explicit representation for the Laplacian of a function in spherical coordinates. So we'll take my curvilinear coordinates to be spherical coordinates. Theta 1 is radius, theta 2 is theta, theta 3 is phi. Here's the graphic representation of the coordinates. So we have a point in space, and we can imagine passing a sphere through that point in space centered at the origin, let's say, the origin of our Cartesian coordinate system. So we can think of the x1 axis here as the corresponding to 0 degrees longitude. This would be like in Greenwich, England, for example. And r is the radius of the sphere. So that's the distance from our point from the origin. Theta then is the azimuth, or the degrees longitude, right, measured from Greenwich, England. Theta would be degrees longitude, so that you can associate that with an angle in the equatorial plane. And then, to get latitude, degrees latitude, you specify the angle phi, which is the angle up from the equator. So you locate this point in space using r, theta, and phi, like so. Okay, and of course, on the surface of the Earth, the radius is more or less constant. So the parameters that we use to locate ourselves on the Earth are longitude and latitude, right? And the way we compute the natural basis elements is just using this formula we had in the beginning. Represent the Cartesian coordinates in terms of the curvilinear coordinates, take the partial derivatives and sum on J, where EJ are the elements of the fixed orthonormal basis associated with the 3 Cartesian coordinates. E1 here, E2, E3, and so on. Okay, so for example, so this is for each fixed I, then we have a sum on J. For example, fix I to be 1, then we need to take the derivatives of the Cartesians with respect to theta 1. Well, here, simply from the geometry, you can see that the Cartesian coordinates are related in this manner to the curvilinear coordinates. We take the partial derivatives as indicated, and I'll revert to the r theta phi notation. And we have cosine phi times this combination. We'll call it E sub r, a function of theta. E sub r is simply the radial vector in the equatorial plane, okay, pointing straight from the origin at the angle theta. That's a unit vector. Then we'll have sine phi times the other unit vector, E3. Cosine phi times this unit vector is sine phi times this unit vector. Because these unit vectors are orthogonal to each other, the result will simply be another unit vector. In fact, you can see that that unit vector will simply be E sub rho. We'll call it E sub rho, which points straight up into space. If you're on the surface of the Earth, you look straight up. The unit vector in that direction is E sub rho. So G sub 1 is a unit vector, pointing straight up from the origin. G sub 2 is the theta 2 derivative. That's the theta derivative. You get this combination. This parenthesis is another unit vector. It's perpendicular to ER. It's also parallel to the equatorial plane. We'll call it E sub theta. It's this vector here. And from any point on the surface of the Earth, it points in the direction due east. it's multiplied by this factor r cosine phi, so the result is G2 is not a unit vector. E theta is a unit vector, but G2 is not. G3, we do the same operation, take a derivative with respect to phi, which is theta 3, and we get this combination of terms. Here's our ER again. So we get cosine phi E3 minus sine phi ER. That combination, so if phi is positive, for example, we're in the northern hemisphere, this minus ER will point inward, and then there'll be a component that points upward also. The result is R times a unit vector E phi, which points from any point on the globe to the North Pole, right? Unit vector. So this, again, G3 is not a unit vector. We can now form the metric by taking dot products of all these G's with each other. For example, the 1,1 entry would be G11, G1 dot G1. G1 is a unit vector, so you get the number 1. G1 dot G2, these vectors are orthogonal to each other, so we get 0. G2 dot G1, by symmetry of G, is also 0. G1 dot G3, these vectors are all orthogonal to each other, so we again get 0. G2 dot G2, we get this dotted with itself, r squared cosine squared phi, etc. Here we get an r squared. So here's an example in which the metric is a purely diagonal matrix with zeros in the off-diagonal entries. Any such matrix, whenever the matrix of metric coefficients is purely diagonal, we are dealing with an orthogonal curvilinear coordinate system. That simply means that the basis elements are mutually orthogonal. If you remember that the basis elements point in the direction of the coordinate curves, that just means the coordinate curves intersect each other at right angles. They're mutually orthogonal curves. So this is a general feature of any orthogonal coordinate system, that the metric associated with that coordinate system is a purely diagonal matrix. Being diagonal, of course, it's easy to invert the matrix. We get this duometric components. To compute something like the Laplacian or divergence, we also need a square root of G, as we've seen previously. So we take the determinant of this and take the square root, that's r squared cosine phi, which of course is always positive, except at the north and south pole, where phi is plus or minus pi over 2. If you remember, whenever the determinant G vanishes, that means that the relationship giving the Cartesian coordinates in terms of the curvilinear coordinates cannot be inverted at those points where that determinant G vanishes. So in a spherical coordinate system, we have two isolated points, the north and south poles of the sphere, where you cannot obtain the Cartesian coordinates in terms of you cannot obtain the curvilinear coordinates in terms of the Cartesian coordinates. But everywhere else in space, everywhere else on the sphere, except at the north-south pole, you have invertibility. That is to say, wherever cosine phi is 0, so that's the entire axis passing through the two poles. Yeah, okay. When we do integration, for example, using curvilinear coordinates, we need the volume measure. We all recall what that is in Cartesian coordinates. It's just dx, dy, dz, or dx1, dx2, dx3. The formula for change of variables in integration theory, we can invoke here. That's just the determinants of the matrix of partial derivatives of the x's with respect to the curvilinear coordinates times the differentials of the curvilinear coordinates. Okay? We've invoked this many times before in courses in continuum mechanics. For example, if we write d small v is jd capital V, that's just an application of this change of variable formula. So this top line here is entirely general. Remember, this determinant of this matrix of partial derivatives is nothing other than the square root of g. So in our spherical coordinate system, this would be square root of g times d theta 1, which is dr, d theta 2 is d theta 3 is d phi. Square root of g is this. So if we integrate any function over a volume and using spherical coordinates, we would multiply that function by r squared cosine phi and then integrate with respect to r, theta, and phi as an iterated integral or a triple integral. Okay, if we want to compute something like the Laplacian, we need the matrix consisting of square root of g, g super ij, as we see here. And we can easily write that down because we have square root of g. This formula, let's do the parenthesis first. We need a sum on j for each fixed I. So let's fix I to be 1, 2, or 3. Sum on j, because this matrix is diagonal, this sum, for example, will just be g11 f comma 1, which is the r derivative of f times the 1, 1 entry, r squared cosine phi. Likewise, this gives only a g22 f comma 2, which is a theta derivative, g33 f comma 3 in this case, which is a phi derivative. In a non-orthogonal system, we will have 3 terms on the right-hand side instead of just 1, right, in general. Okay, so if we collect everything and do what this procedure tells us, now we collect these together and sum on I. That means taking the derivatives with respect to the coordinates. We just get this explicit expression for the Laplacian in spherical coordinates. So this is, if you were to solve Laplace's equation in spherical coordinates, you would be solving this equation equal to 0. While we're on the subject of covariant derivatives, let's return to that discussion. We can prove a very important product rule for covariant derivatives. So covariant differentiation obeys the so-called Leibniz rule or the product rule that we're accustomed to for conventional derivatives. So this is a very important and useful property. Let's demonstrate this by example. So suppose you have this equation for a vector. V is some tensor, second order tensor operating on U. Let's represent that second order tensor in terms of its contravariant components. And the operation on U here gives U dot Gj, which is the covariant component Uj. And of course, some Aij, Uj, G sub I is left over. So this defines then the contravariant components of the vector V in the natural basis. We can compute the covariant derivatives of these contravariant components using our formula from previous formula. That involves taking a partial derivative in the first place, which we take the partial derivative of this combination here, and then we replace Vj by this. I must rename the pre-index J and then the summation index, I'll call it L. Okay. And now what I will do is I will add a term. Let's see. I will add and subtract the same term. I will add this term and subtract it again. You can verify that this term is the same as this one if I simply rearrange the summation indices, which I'm always free to do. And then I'll retain the original term here with, again, a relabeling of the summation indices. So I've simply added and subtracted a term. And then I will combine all the terms in multiplying U sub j together. And I will then multiply together all the terms with coefficients a super ij, like so. The first parenthesis you recognize as the covariant derivative of the tensor A. The second parenthesis is the covariant derivative of the covariant components of U with a minus here. Right? So here we have an explicit demonstration of the product rule for covariant derivatives in this case of a tensor and a vector. Well, you can easily extrapolate this to generate the same covariant, the same product rule for any kind of product. For example, two tensors without any summations taking place. This is more tedious to verify, but it's straightforward to do so. Another useful example is the covariant derivative of a vector formed from a scalar multiplying a vector. That also obeys the product rule, provided we interpret the covariant derivative of the scalar as the conventional partial derivative. And with this convention, you will see that this product rule for covariant differentiation is preserved. Okay, so we will always interpret the covariant derivative of the scalar as simply the partial derivative, so as to preserve the product rule. Okay, let's return to our discussion of the divergence of a vector. We wrote that this way, v super I, and then recall I mentioned that v super I can be written g super ki vk. So now we have something similar to what we've just had here in this expression. This is essentially a matrix times a vector. We can invoke the product rule and invoke the fact that the covariant derivative of the dual metric is 0, as we've discussed before, and then we have this result. So the net effect is that the covariant derivative does not see the dual metric. In other words, the dual metric has no covariant derivative, so we can commute the property, the operations of raising an index using the dual metric with the covariant derivative operation. Okay. The Laplacian, likewise, we can write this way. We can have the dual metric inside or outside. And the same with operations involving the original metric with subscripts. That metric is also constant with respect to covariant differentiation. In your next homework, you will prove that the covariant derivative of the second order tensor is itself a third order tensor. And you will prove a transformation formula for third order tensors. That transformation formula says, will enable you to prove that if a third order tensor is 0 in one coordinate system, it's 0 in all coordinate systems. Well, this object here, Gij semicolon k, we've already seen that that's 0, but another way to prove the same thing is to notice that in a Cartesian coordinate system, which is admissible in our Euclidean space, in a Cartesian coordinate system, the metric is just the unit matrix, right? Because the derivative of position with respect to the Cartesians are just the fixed orthonormal basis elements. And the connection coefficients are 0 in a Cartesian system. So this simply reduces to this, which is 0. Now, if we transform to a different coordinate system, this gets transformed to this. And the coordinate transformation formula, you will show, ensures that if this is true in one coordinate system, which we've just seen is the case, it's true in a Cartesian system, then it's true in every coordinate system. So in fact, that's an alternative way of proving the Ricci lemma, although we've already had a perfectly satisfactory proof of this without using any coordinate transformations. Another interesting result, and then I'll stop, Remember our third order permutation symbol. We can prove that this is a third order tensor, that this covariant derivative is in fact a fourth order tensor. If we transform that fourth order tensor to Cartesian coordinates, we will get E sub ijk comma L, which is 0, because E sub ijk is 1, 0, or minus 1, they're constants. So this is true in a Cartesian coordinate system. The tensorial property of this object on the left-hand side guarantees then that this is true in every coordinate system. So this equation is more difficult to prove than the Ricci lemma, the vanishing of the covariant derivative of the metric, but we can prove it nevertheless using simply the tensorial property of the left-hand side. Okay, I will stop at this stage and we will resume on Thursday. Thank you.